engineers and some security people and some application people at AppSec. I am both, and I also run a security program for a startup in San Francisco. Today I'm going to talk about how to protect data or do encryption the right way. Hopefully a lot better than I can get a new MacBook to project on slides. So this is a typical setup for a web application on the internet. The internet connects to a web server connects to a database. You have a lot of secrets in that database that you want to protect. The problem that we keep seeing is this is a crazy model. This is like we take our most expensive valuables, maybe a diamond ring, we stick it in a safe, we put it in the trunk of our car, we drive our car out to the worst neighborhood you can find, the internet, and we leave it there and we hope it's safe. Any compromise in that web server has credentials in that database, can pull the data out. We've seen this happen over and over again. So what's the situation? As we look at across the spectrum, knowing that we have application security people here, these are all probably pretty well-known attacks I'm going to go through quickly. So in 2014, Anthem Blue Cross discovered that they had lost 37.5 million health records because a database admin logged into the database and saw that he had logged in the night before when he wasn't anywhere near his computer. It took a year for them to discover that they were breached in the first place. And the findings, the report that the government issued on this company afterwards said that they had best-in-class security. They exceeded the security of other people in their space. Like, they couldn't find anything wrong with their security program. It wasn't a problem with their security program that made them lose their data. The Equifax breach, I mean, we're really familiar with this one. This is exactly what I was talking about. A single exploit on the web server can literally happen to anyone. Yes, they could have patched earlier, but I think a lot of companies miss patches on some servers and they don't discover it until months later, and then they fix it. And that's how the world works. But one vulnerability on a web server exposed 300-something million records through Equifax. So it's a low barrier. It's hard to protect that. The Verizon data breach investigation. Breaches aren't discovered for months in 96% of the cases. Most of the time, they're actually discovered by somebody from the outside who noticed that some data was leaked. I mean, this is Brian Curbs. This is hey, the credit card company is calling you and saying that you're the source of compromise for a lot of credit cards. So we don't monitor data very well. Best companies keep getting breached. Our architecture is not secure to begin with, and we don't monitor data very well. I think, though, the real issue is what it boils down to is we don't even know if we're safe. I mean, as a head of security, I have people asking me, like, are we safe today? Like, what's the chances of us being breached, or are we already breached? And I have to tell you, I think everyone in this room shares the same fear that you don't actually know if you're breached. You could have a bad guy in your network right now and not know about it. And that not knowing can keep you up at night. But there may be some solutions to this. Is anyone paying attention? This blockchain, right? That's a solution? It's not the solution. The solution is encryption done right. So my theory, the premise is that if you have cryptography around your data that helps you defend it and identify who's accessing it, then you have a really great signal whether or not you've been breached or whether or not your company is safe. So quick outline where I'm going to go through. Talk about the goal, it's keeping data safe. The problem, we don't know if we are safe. Some of the challenges of protecting the data, the solutions. I'm going to go through most cryptographic solutions or techniques that we use. Not like AES versus RSA, but more of the crypto system and how you as a non-cryptographer can analyze it. And the last one, which is what is this crypto anchor that I've been talking about. So the challenge. This is our challenge. At first, it doesn't look that hard to protect, but then you start adding all the people and all the different roles that have to access this environment. You've got on the bottom system admin, database admin, you have your developers, you've got a build and deploy stack that pushes new code out, you have users that access it from the internet, some Salesforce, some admins out there. All of those people, they also have laptops, and you have to incorporate all the vulnerabilities in their laptops as well. Have they been exposed to phishing? Have they installed malware on their laptops? What else is going on with those laptops that now have access to this data? Then you have to realize that those laptops are managed by IT. So the IT people also have access to those laptops. They can compromise those laptops. They can remotely control those laptops. And so while you may trust your sysadmin, you may forget your IT guy that you're about to terminate also has access to this environment and could have left backdoors in place. Hackers got access to all of these people and all of these devices. You also run it on Amazon Web Services, so you have your credentials for that environment, right? So your management console or your access keys. You're also backing up your database somewhere. So there's a copy of all that sensitive information that you want to keep safe. And then you have the policy police, right? The people that come in and say, hey, are you rotating your passwords? Are you meeting all the compliance and policy things? So these are all the concerns that you have in addition to just keeping that simple data safe. We're going to go through these 6 challenges, the ones that have the star on them. So compliance, you've got AWS Management Console, and these are going to be threats. Like these are the threats to the system, the most obvious threats. Compliance is only on there because it fills out a row. It's a checkbox for me as well. The AWS management compromise, that's a big one. I mean, with AWS credentials, you can do so much work, so much damage that I'm not a big fan of one single point of failure. And I believe that if you don't architect your systems well, AWS is a single point of failure in terms of the management console. So we'll go through these a little bit more. You have a server admin, database backup, database admin compromise, and application compromise. Okay, great. So those are the challenges. The next step is we're going to look for the solutions for how we're going to defend our networks against those challenges. So let's talk about encryption. Encryption done right. So encryption's essentially you get ciphertext by encrypting plain text with a key. You get plain text by decrypting ciphertext with that key. So you always need, so what we're really focused on is how do you recover that plain text. You need both the ciphertext and the key. Now if we could keep the data or the plain text secure in the first place, we wouldn't need to encrypt it. So what makes us think we're going to be able to keep the ciphertext safe? Probably not. But we do need to be able to keep the key safe. So if you have to pick one, either the key or the ciphertext. And the way crypto works is you want to keep that key safe and let that ciphertext go wherever. So when you're analyzing a crypto system, you're really looking at where that key is, who has access to that key, and how you can protect that and monitor those keys. Okay, so I'm going to look at these 5 techniques for doing cryptography. The first one is Amazon Web Services has a checkbox where you can turn on encryption on the hard drive. The second one is where you have your operating system perform the cryptography. And this can be BitLocker on Windows or the Lux file system on Ubuntu or Linux. The third one is database implemented encryption. So this is where your SQL server or your MySQL is actually doing the encryption operation at some field level or during your SQL statements. The fourth one is application encryption. So on that previous diagram, this would be the web application. So the encryption happens before the data goes to the database. And the fifth one is the crypto anchor, which we'll get to for the rest of that talk. Okay, so looking at the first one, which is hard drive encryption through Amazon Web Services. Basically, you start off with the physical servers, you have a virtual server on the left. The data, when the virtual server goes to write data to the disk, it's in plain text. It sends it to the virtual hard drive. Amazon intercepts it. It encrypts it using a KMS key, and then it takes that ciphertext and it writes that actual ciphertext to the physical disk. And so what this buys you, so this chart here, on the column, we have the 6 different types of encryption we're going to go through right now. And then, on the column, we have the 6 different threats, or the challenges that we talked about a minute ago. And then on the top, we're looking at the 5 different types of encryption. So the first one's AWS hard drive encryption. And you can see that the one threat or the one challenge it meets is that it meets your compliance requirements. In honesty, I think the other challenge it meets is there are actually 2 other challenges, which is when you're on AWS, when you write data to a disk, and then you shut down that server, you don't want the next customer to come and see that data, right? So you want that data to be scrambled so that the next customer can't see the shared data. The truth is, AWS already wipes their disks. They solved this problem a long time ago. They thought about it already because they didn't want customers to see their data. And the other one is, this also protects when somebody goes into a data center and removes a physical disk. But again, AWS handles this by destroying their disk before they leave the data center. So practically, this meets a compliance checkbox today. Okay, let's look at operating system disk encryption. So in this case, you boot up a server, you give it a key. That key you don't store the key on the disk because that would be crazy. If you store it on that disk, then somebody could take a backup of the disk and recover the key and decrypt the data. You have to keep that key in memory. You can't write it to disk. So you boot up the server, you type in the key, and now every time that server writes data to its disk, it runs it through a software encryption so that only ciphertext is written out to the hard drive. The key doesn't leave memory. And so what this buys you is you now can protect yourself against somebody that steals Amazon Web Services credentials for your environment. So before, when you're doing this first one, which is AWS hard drive encryption, if I was an admin on your AWS management console, I could take a snapshot of your disk, and I could see all that data because I have access to the key. The key is stored with KMS. As an admin, I can use all those keys to decrypt data. So that's why it didn't protect you from an Amazon management console compromise. However, with an operating system encryption, because the AWS service doesn't have that key, you're protected from this threat. And that is really important for me because, again, I don't like Amazon admins being my single point of failure for my entire security posture. Okay, let's look at the next one. Database encryption. I'm not going to go into too many details about this because there's a lot of databases out there, and they all do it a little bit differently. But fundamentally, most of them have a key internally that they have to persist somehow. And when they persist that key, it's going to get written to disk. So when you take a copy of that disk, you have both the encrypted data and a key to decrypt that data. Fundamentally, that doesn't buy us very much. It protects the data from a few use cases, maybe. And again, it depends on how it's implemented and how it's configured. So we're just going to say maybe for these next 2 threats, which is the database admin compromise and the database backup compromise. Again, it depends on how you back up the database, where the key is stored, all those things. But let's move on to the next one. This one's application encryption. And the idea here is that you never send the plain text to the database in the first place. You only send ciphertext of the sensitive data to the database. Now, I'm not saying that you encrypt every single thing you store in the database. You'll take something like a social security number or a credit card number, the sensitive information, or even a password hash, like a decrypted password hash. You would encrypt that before you store it in the database. Because that way, if somebody steals a backup of the database, unless they also have the key that's stored on the application, they can't recover the data. And that's the goal we're going for. So there's some definite advantages to moving that key away from the database entirely. Now you can protect that key separately from the data, the ciphertext. They're completely different threat models at this point. You can protect the database, who has access to the database, entirely differently than you have to protect that web server and who has access to that web server. So that gets us down this chart. Now we have server admin compromised would be a database server admin, or somebody who has access to like the backups of that database. I wouldn't necessarily protect us from the person that has the web server admin credentials, because they have the key and maybe they can get a copy of the database. But it still doesn't protect us from an application compromise, right? And that's what we're here for. How do we do that? So application compromise is going to be the next one. This is where we're going to talk about the crypto anchor. In this scenario, we take the key and the encryption operation and we move it to a microservice. So now neither the database or the application server have the key, and neither one of them are doing the actual encryption and decryption. And the reason this is important is because, again, if you can get that key, then and it's going to be easy for you to get a copy of the data. And if you get that key as well, you can take the data, you can decrypt it at your house. You can decrypt it anywhere you want. But what we need to try to do is force people, as a developer, and this is a common practice, you might even download a copy of the database, decrypt it locally, and start playing with the data. Because sometimes you just need to do that. But in this model, you can't do that. There's no way for you to extract the key. So let's talk about, so basically crypto anchor is the only one that protects against all these threats. Encryption done right, to summarize, we need to use a crypto anchor to meet. The only way to actually know that you have a good encryption technique is if it meets all the threats in your threat model. And what we found out is that the crypto anchor needs to do these three things. You can't decrypt offline, you have to limit access to the keys, and you have to log what's being decrypted. Okay, so the crypto anchor. So the way it works is the web server has something it needs to store in the database, maybe the social security number. It sends out plain text to the crypto anchor. It says, encrypt this. The encryption service logs out to the log system that says that the web application has encrypted this social security number at this time. And then it sends back the ciphertext to the web server, and the web server sends that ciphertext to the database server. Now the database server only has a encrypted copy of that data, and we have a log. The reverse of this is decryption. The web server goes and gets the encrypted social out of the database, sends ciphertext to the crypto anchor. We get a log that says that this social security number is decrypted at this time by this service, and then the plain text to return the web server. The real trick in this crypto anchoring, the reason that this protects your web application, is the logging. So the cipher that we're using for encryption is an authenticated cipher. It's actually AES-GSM. And I don't know how to say what that stands for, but what's important with it is you send actually three pieces of information to the crypto algorithm. You send the plain text, you send the key. Actually, I'm sorry, the web server doesn't send the key. The key's managed by the crypto anchor. The web server will send the plain text and a description of what's being encrypted. And that description should be verbose. It should be verbose, and it's going to be logged. And the whole point is the description is logged. So you can say John's social security number, and then you know what is actually being decrypted. So in the first example, this is a normal encryption. You get a timestamp, you get who decrypted it, you get the size of what was decrypted, you see what the key was. It's not very informative. It could be anything. It doesn't tell you what was being decrypted or encrypted. Versus authenticated ciphers, you get the person, you get the size, you get the same information, but you also get that context. You see the record ID, you see the record type was a credit card number. On the second one, you see the record ID. You see it was an email address. So we can start to make theories about whether or not Tom should be encrypting email addresses. We can make theories about whether or not Bob should be decrypting credit card numbers. You couldn't do that before from your database. You couldn't do that anywhere else in your environment, but now you can actually start to profile who's doing what with your data. How many records is Bob decrypting? If you're Equifax, how many records per hour do you normally decrypt? Do you normally decrypt 300 million records in an hour, in a day, or in a week? Or is that outrageous or something you need to investigate? Maybe after 1 million records in an hour, you shut down the service. So that's basically the key to the logging piece. This is how you can defend against application compromises. The other piece, the other reason this is, the way that this works is you have to force people to come back to your data center. The reason it's called an anchor is because it anchors the decryption process to your data center. You can't extract the keys from a good microservice. You can't take those keys and use them offline. You have to come back to the data center, which means you're going to get the logs every time that a record is decrypted. And with those logs, again, you can profile whether or not they should be doing this, and you can set off alerts as to whatever the threshold is for that service. You also use this for other encryption things, like maybe all of a sudden John starts decrypting all the API keys, and that might be a problem, right? Maybe I went rogue or I got hacked, and now I'm decrypting a bunch of stuff I shouldn't be decrypting. But we actually have records of the information I've accessed now. So I have a couple of minutes. I'm probably going to go 5 over since we got started late. I'm going to talk about the 3 ways that we can implement a crypto anchor. First one's a hardware security module. What that means is that the keys are actually stored in silicon on some piece of hardware. It's not possible to extract those keys off of that hardware. So this meets that property where you can't pull the key out of the service. You have to come back to the HSM to decrypt your data. That's the strongest guarantee you have. The next one is a common crypto system is Amazon AWS. Now using KMS from AWS as your crypto service, you get everything we just talked about, with the one drawback that your Amazon admin also has access to these crypto primitives. And so again, if our threat model includes an Amazon admin being compromised, KMS is probably not your first choice. The third one is HashiCorp Vault. HashiCorp Vault is my favorite. It's a microservice. The way you defend it is you only give like 1 or 2 people in your environment access to it. The keys could be theoretically extracted if you can log onto the machine, pull them out of memory, which would kind of defeat the entire crypto anchoring solution. But at the same time, if you only have a couple of people with access to this machine, you also can monitor who's accessing it when they're accessing it and have a heightened alerts on that kind of situation. So the way Vault was architected is you don't get the keys out of it unless, well, yeah, you have to get memory access to get the keys out of it. Nobody else has the key, so by default, you don't pull the keys out. By default, you send all your data to it. It encrypts it and sends it back to you. So I think the takeaway from this talk is to go out and get Vault, play with it. You can download it, you can run it, you can look at the logs, you can see the benefit of logging out context with all of your encryption, decryption operations. And yeah, these are some quick instructions. You can reach out to me and I can give you more detailed instructions that we've set up for this. So to summarize what a crypto anchor is, logging is the key to protecting the data. you have to bring the data back to the data center, so it's a choke point. All of your encryption, decryption have to happen on this service. That gives you the benefit that you can log, and you always know when your data's been accessed, which is really hard to do on that other, in the world we live in otherwise, with all the different people who can access your database. This is the only way you can actually tell who's accessed your data. And the last item here is that you can profile normal behavior, and you set thresholds for abnormal behavior, and you can take actions against that. All right, so that's it. Thank you for coming to the talk.